Who is going to talk about impact of ion neutral predictions in fluid models and machines. So 30 plus 50.
So hello everybody. I'm a freshman in the community since I defended my thesis last year, and I started my postdoc and will be working on turbulence and in Institut JHMun. And unfortunately, I don't have really directly related turbulence results. And the presentation will be more focused on the work I've done during my PhD and how is it related and how did it allow me to be introduced in this community. So for the context, actually, when you do some direct current glow discharge in a moderate pressure range, about 10 to the 100 Pascal, it can be used to grow nanoparticles inside the reactor. And the cathode sputtering is generally the main source of matters for nanoparticle growth. And the main mechanism of these nanoparticle growth happens inside the cathode sheath. So in order to correctly model this phenomena, the laboratory of Marseille wanted to have a code that was capable of simulating the cathode sheath, but using a fluid model. So why fluid model? Because usually when you do simulations in this field, the numerical tools are based on the kinetic of fluid description. The kinetic approach gives the evolution of a distribution function in the phase space. It has the advantage to be very precise, and it can describe the physical mechanism at play in the velocity space. But the drawback is that sometimes it's difficult to directly interpret the results, and it is very, very time and memory consuming. On the other hand, the fluid approach is a reduction of the kinetic approach by integrating in the velocity space. We deal with averaged quantities. So the advantage is that you directly get more intuitive physical quantities to interpret, and it is faster and much lighter compared to kinetic codes. However, since you integrate over the velocity space, the drawback is that you lose some informations, and you need some closure approximations to get a model. And the focus of my PhD work is that we wanted to show that the fluid models can be improved by adding appropriate physical ingredients. And it can also be used to accurately simulate a plasma sheath in a DC discharges. And the other focus of my work is the ion neutral collisionality level. Usually when you do cold plasma simulations, you are in the collisionless regime. And there you assume energy conservation of particle inside the sheath. And also, typically the ion temperature is assumed to be constant, thermalized at the neutral temperature level. On the other hand, you have the collision-dominated regime, which is usually observed in high pressure discharges or in bulk plasmas, where once again the ion temperature is thermalized to the neutral background temperature via collisions. But we found that under the discharge operation conditions that we adopted during my PhD work, we were actually in the transitional regime. And in this regime, there are collisions, but there are not enough collisions to completely thermalize the ions. So we observed a widening of the distribution functions that implied an increase of the thermal energy. And we also observed non-Maxwellian sheets, non-Maxwellian distributions inside the sheets. So now I'll be presenting very briefly the code framework and the first plasma fluid model that I developed during my PhD. So why did this work took my whole PhD is because the laboratory wanted to write a very new code, starting from the scratch. They wanted an in-house code that they have all the possibility to tune it as they wanted. So we started in a very simple discharge geometry in a 1D, a DC discharge without magnetic field, only one electron and one positive ion species. And for simplicity reasons, we took a fourth order or third order Runge-Kutta explicit method for time resolution. And the spatial discretization was done using second order center spread, a finite difference scheme, but with a staggered grid configuration for numerical stability. And also for the fluid model equations, we took the typical ones that were used for cold plasma simulations. The continuity equation, that stands for both electrons and ions. And the electron momentum equation was transformed into the electron drift diffusion flux, which is also a typical assumption done in the cold plasma simulations. For the ions, because of their heavy mass, we solved the ion momentum equation. The energy equation is solved for the electrons only, and the ions are assumed to remain at 300 Kelvin all along the simulation, which is also a typical assumption done in cold plasma simulations. So at the beginning, we thought we would have thermalization due to collisions in the bulk plasma and a collisionless sheath that is typically observed in the cold plasma simulations. And finally, we added the Poisson's equation because we wanted to simulate the sheath where it is expected to see some development of space charge. And in order to solve this fluid model, you need these transport coefficients to be you need these transport coefficients to solve the equations. So what we've done is that we use the electron argon gas collision cross sections, and we integrated over it to obtain all the necessary transport coefficients. Yes. The electric field is just the gradient of the electric potential that's obtained via the Poisson equation. Yes. So this model is not the quasi-neutral model. So we solve the Poisson equation, we get the electric potential, and then we derive it to get the electric field. And for the ions, what we need is collision frequency. And we use this formula and the experimental mobility database that was measured at the room temperature. So this database gives the mobility as a function of the electric field. Then we use this formula to get the corresponding collision frequency. So the first test simulation was done using these parameters that were taken from the original glow discharge operation conditions. So this is a 1D fluid discharge simulation, including the sheath. And for the moment, the background gas temperature fixed at 300 Kelvin, as well as the ions. So these are the first fluid plasma discharge profiles we obtained. So in the upper left corner, you have the electron density and the ion density profiles. So you have the anode here in the left and the cathode here in the right. So we have the anode sheath here developing, and then a bulk plasma region and a huge cathode sheath region just in front of the cathode. Down here is the electric potential profile that was given by the Poisson equation. So it starts at the anode. Anode, we have a flat top here in the bulk plasma region and the cathode fold here. Here in the blue is the electron mean energy profile. We can see that the electrons are heated only inside the sheath due to the presence of intense electric field. And in the red, I plotted the the continuity equation source term, which is the ionization source term. And finally, in the lower right corner, I also plotted the ratio of the ion velocity calculated by the model over the bomb velocity. And we can see that these profiles do not correspond to the expected theoretical cold plasma discharge profile. Although we have a qualitative agreement in the plasma potential profile, when we look at the cathode sheath density profile, we observe that the ion density actually re-increase inside the sheath rather than just showing a monotonical decrease. And also, when you analyze these electron energy profile and the ion velocity profile, we observe that inside the sheath there is a non-zero collisional source term of charged species, and also the ions never reach the bomb velocity before exiting the plasma in the cathode. So we could see that under these operation conditions, our plasma do not agree with the collisionless sheath theory. But before going further, we wanted to validate the code with the already published results in the literature. So we found some other fluid model presented in the literature. We took the simulation parameters that were presented in that paper and we ran the code again. And then when we compared the density profile, we could observe that even in those papers, the ion re-increase, so the ion density bulge inside the cathode sheath was observed. So we had qualitative agreement with the already published results. However, we also had a pick code inside the laboratory. So as a last step of validation, we also launched the same simulation using the pick code for validation purpose. So the treatment of collisions is actually slightly different in the fluid code and the pick code. In the fluid code, you pre-compute a collision frequency that you inject inside the equations. However, in the pick code, you can use directly the collision cross sections. So you can activate what kind of collisions you want to see inside the model. At the first step, we only activated the ion neutral elastic collisions. And after, we also activated the charge exchange collisions, but I will first present the elastic collisions only results. So here I plotted together the pick code results and the fluid code results for comparison. We can see that for the plasma potential and the electron energy profile, we have more or less agreement between those two models. But there's a huge discrepancy that was observed in the ion profile. For example, in the pick code, there's no ion sheath density accumulations. And also the sheath width that was predicted by the fluid code and the pick code were different. And lastly, the ion sheath exit velocity was much, much higher in the pick code. So we saw that there's huge discrepancy in the ion profiles. And the pick code we used for simulations had 1D, 3V configurations. So it offered us the possibility to investigate the ion velocity in all three dimensions. The X dimension here is actually the main direction. And the Y and Z, I will call them now the perpendicular directions. So with the cathode in the right here, when you observe the ion velocity distribution just in front of the cathode inside the sheath, then we observe that in the perpendicular directions, we have a zero-centered symmetric distribution. But in the parallel direction, we have a very asymmetric non-Maxwellian distribution function. Also, in all the three dimensions, these distribution functions show a widening. That means a non-negligible thermal heating of the ions was happening inside the sheets. Here is the plot of ion total energy and the ion thermal energy. We can see that with the cathode in the right, inside the sheath, we have up to 10 electron volts of ion thermal energy, which is really not negligible compared to the room temperature here at 300 Kelvin. And also, there is an anisotropy that appears inside the cathode sheath because we can see in the perpendicular dimensions, the Y and Z temperatures are the same. But in the parallel direction, the X temperature is much higher. So now we needed to think about how to implement these discrepancies in the fluid model. So first, rather than just assuming a cold ion in the whole reactor, we have to solve the ion pressure equation. But we start from the isotropic pressure equation, but we introduce a scalar but anisotropic pressure assumption as a first step of improving the model. We still assume that the pressure tensor is diagonal. There's only three components, but there's two different components. There's the parallel pressure and the perpendicular pressure. And the total scalar pressure is the sum of these two contributions. So when you inject this assumption inside of this isotropic pressure equation, we can isolate the parallel pressure to get a parallel pressure evolution equation. And also, we saw that the perpendicular dimension is also heated well above 300 Kelvin. But as a first step of a test and improvement, we assumed for now that the perpendicular dimension remained at 300 Kelvin. So solving this equation, we assumed also a heat transfer. Since we saw that there's non-negligible collisionality inside the sheath, rather than just using the Fick type heat transfer assumptions, we assumed that collision-dominated heat transfer in this form. And finally, the collisional, the pressure source and sink term was assumed to have two contributions. The ions are heated via frictional heating, and also they are relaxed by collisions with the neutrons. So at the beginning, we found in the literature a work that proposed an empirical formula of the ion mobility as a function of the ion temperature. So to be simple, we just wanted to keep the formula for the calculation of the ion neutral collision frequency. We adopted this empirical formula and injected the ion temperature that was calculated by the fluid model equation. And the fluid model with the self-consistent ion temperature calculation showed a huge improvement compared to the cold ion assumptions. So we can now see that the sheath width and the ion sheath density profile is now corrected and very similar to the one predicted by the Pick code. Also, the ion sheath exit velocity has now a comparable order of magnitude compared to the predictions of the Pick results. But however, later we got some comments on the published results that the ion mobility should be lower. The higher the electric field amplitude is, the lower the ion mobility should be. But using the empirical formula, this was not verified inside the model. And also, since the ions are heated, when you observe the cross-section here, for the energetic ions, actually the charge exchange collisions with the neutrals prevails over the elastic collisions. So we need to find a new way to implement the charge exchange collisions into the fluid model. Because even in peak model, just the fact that we activate the charge exchange collisions changes a lot the results. Especially, it slows down considerably the ions inside the sheets. However, even with those slowed down ions, the ions were still heated considerably. So we just needed to find a way to put the influence of charge exchange collisions inside the fluid model. So the first approach was just to integrate over the using the cross sections. But in order to do this, we needed an assumption on the ion distribution function shape. We already know that there will be an anisotropy. We also saw that in the parallel direction, it was highly asymmetric. But once again, one step at a time, we assumed that there was a shifted Maxwellian distribution function in the parallel direction, and the other perpendicular direction remained just zero-centered Maxwellian with a fixed temperature. So using this new distribution function, we integrated over the velocity space using the cross-section of the collisions, and we applied an effective collision frequency that was the sum of the elastic and charge exchange collisions. The result was once again surprising, because we know that we did very rough approximations when we wanted to implement the anisotropy and the charge exchange collisions into the fluid model. But even with these very rough approximations, the fluid model showed once again that it was capable of reproducing very similar results compared to the predictions of the peak model. So this result shows that with the appropriate physical ingredients, fluid models can do shear simulations. And the shear simulations is important in the boundary plasma studies, because when you have a boundary plasma wall interactions, there's inevitably development of the shear regions. So after defending my thesis with these results, I was recruited in the Institut Jean Lamour in Nancy to work on the Spectre machine. So the Spectre is a huge linear configuration machine, and Spectre stands for shear plasma edge kinetic turbulence radio frequency experiment. So it's a huge project that was going on there for several years now. And this is the latest photo of the machine took on June 2025. So it's a huge linear machine with the inner cylinder diameter of 90 centimeters, with the magnetic coils out there coming from Stellarator from Germany. So it uses a helicon source chamber here and uses the coils to create a magnetized plasma environment inside this long column of total 7 meters of length. So it is intended to have two discharge modes. The hot plasma mode will be around a pulsed mode with a very high magnetic field. It will be used for many purposes, but especially to study the fundamental aspect of turbulence and the turbulent transport in magnetized plasmas. So we finally got the first plasma last April without magnetic field for now. But the first experimental campaign should start in early 2026. So there are many things that are programmed. And my contribution will be focused on the numerical simulation of kinetic and fluid using fluid codes. The JHMun code, which is the code I presented in this work, it will be expanded in RZ 2D configuration. But I will also use the Bout++ code in R theta configuration to observe the turbulence that will be driven inside the machine. So as a conclusion, starting from scratch, a 1D fluid DC discharge model, including plasma sheaths, has been developed. It was validated using with the published results. A non-negligible ion heating was observed in the kinetic simulations for moderate pressure range and intermediate collisional regime inside the sheath zones. And the addition of the ion anisotropic pressure equation helps to improve the fluid model results with respect to the peak results. It showed that the fluid model was capable of reproducing accurate sheath simulations. As a perspective, I will continue to implement other inelastic collisional processes. And as it was highlighted yesterday, when you involve charge exchange collisions between the ions and the neutrals, in order to properly implement it, we have to implement the neutral mechanics inside the model. And also, a shifted truncated distribution functions will be studied for calculating the collision frequencies inside the sheaths. And finally, the model, this fluid code will be extended in a 2D RZ configuration to be used in a SPECT machine simulation. Thank you for your attention.